just going to test. Okay, do you hear me? Ah, nice. Okay, yeah, so my name is Wissing. So I am a first-year PhD student at the University of Oslo. My supervisor is Sijing Shen. And today I will talk about SPMHD with the geometric density force gradient operator. However, I will just call it the GD force operator. So before I get into that, I will talk a bit about the background of magnetic field in galaxies. So here you can see the synchrotron radiation from Planck, which shows the effect of the magnetic field in our galaxy. So how are magnetic fields generated? Well, first what you need to do is to have some sort of seed field. And those are generated by several different processes, such as Weeble instability or plasma instability. And the subsequent amplification is due to turbulent dynamo. And this amplification will continue until the magnetic energy reaches equipartition with the turbulent energy. So whatever sort of seed field you start with, you usually get up to the equipartition. So there have been several simulations of galaxy formation, including MHD. And both Wang and Abel and Packmore and Springle showed in their simulations that you do get a suppression in star formation. However, Su and others recently showed that there was no reasonable big effect due to magnetic fields in isolated galaxy simulations. And this might be due to them using a much stronger feedback model. But something that has been shown is that magnetic fields have a strong impact on fluid instabilities. So here you have a cold gas blob being accelerated by a hot wind. In hydro, the gas blob is fully disrupted, while in MHD, most of the cold gas is still intact. And finally, we saw just a couple of talks ago that Irina showed that cosmic rays can drive galactic outflows. However, to correctly transport cosmic rays, you need MHD. So the method that I used in MHD is SPH+MHD, which is smooth particle hydrodynamics, smooth particle magnetohydrodynamics. And in this method, there has been many improvements in the recent years. So first of all, there has been the introduction of new kernels, which allows us to increase the number of neighbors, which reduces the noise and improves the convergence of the method. Another thing that has been very big is the modern switches that have been introduced, which reduces the dissipation away from shocks. And there has also been a lot of work done on the divergence cleaning of the magnetic field, as we always have some numerical divergence created in our simulations. And another thing that has been a big problem in SPH is the suppression of fluid instabilities. And that was shown by Agert in 2007. And the two big reasons that causes this is a surface tension effect that happens in density jumps, which effectively creates an unphysical force between the two surfaces, and also that there is insufficient mixing in SPH, and this is due to unresolved turbulent diffusion. So there has been some different solutions to the problem. For example, Ritchie and Thomas suggested that we smooth the pressure instead. However, this can be very noisy. Artificial conductivity was introduced by Price, which does not really work when you include gravity, because you get dissipation even in hydrostatic equilibrium. And then the pressure entropy SPH, which Hopkins introduced. However, I don't know, however, I will show later that you do not really alter the MHD equations when you do this, and in some problems, this formalism doesn't help. So last year, Gasoline 2 came out, which introduced the GD force gradient operator. And basically, what it is just a different gradient operator. So here you can see a more generalized form of the gradient operator applied on the momentum equations. And here a sigma equals to 1 is equal to the GD force formalism, and a sigma equal to 0 is the traditional SPH. And Monahan and Raffi has in 2012 shown that this is derivable from a Lagrangian. And it was shown in the gasoline 2 paper that this basically solves the fluid instability together with turbulent diffusion, a subgrid turbulent diffusion. Okay, so up here we can see the classical SPH. Basically, so this is a blob accelerated by hot wind again. So basically we can see that there is no Kelvin-Helmholtz instability being created, so the cloud is not disrupted. However, if we just add the GDF, we see that we get disruption, however, not very good mixing. So adding diffusion adds this mixing. Okay, so what I have done is to implement the ideal MHD equations with the GDF force operator. And I have also included the new artificial resistivity switch developed last year by Price, and also the constrained hyperbolic divergence cleaning by Tricco in 2016. So I will show some of the test cases that we have tried, just a few of them, because I don't have time. So the first one I was thinking of showing was the circularized polarized alpha wave, which is an analytical solution to the ideal MHD equations. And in SPH, we do not if we don't add any dissipation, we don't have any dissipation. So we would basically get the same solution every time. The same after each period, we would have no dissipation of this wave. However, we need to add dissipation for shocks. And what we find is that we have a second order convergence in resolution. Then we took a look at the magnetic rotor. And here we do see some differences between GD force and the traditional SPH. So, and the magnetic rotor is basically initiated by having an ambient medium and a more dense, and a dense rotor that is, the whole thing, there's a uniform magnetic field put on here. The rotor rotates, and due to rotation, it winds the magnetic field, which creates torsional alpha waves. So it's a good way to test that. So here we see that there is a big density difference at the surface between the two mediums. And the reason to this is due to the reduction of the surface tension. In GD force, we see we don't have it. In the classical, we see it. And what this effectively also works out to be is that we have, it's very hard to say though, but we have an application in the GD force of magnetic energy, especially in this magnetic pressure high here. It's very subtle though, but it's still visible. But where we see the biggest effect is in the magnetized core collapse. So the magnetized core collapse, so we initialize it with a cloud that is rotating and is magnetized, and then we have an ambient medium, and we then allow this cloud to collapse, and the collapse is halted by the formation of a disk, and due to the winding of the magnetic field, we get the launch of jets. So here we see a big difference. In GD force, we get the jets, and TSPH we don't get. Oh yeah, I was going to also explain why the mu is. The mu is basically the mass to flux ratio over the critical mass to flux ratio. And so basically mu equals 1 is a cloud that is completely magnetically supported. So it balances with the gravitational forces. And I also wanted to just compare a bit with the Hopkins and Ray's paper, which also tested this case. And you can see that in the PSPH that they use, we get the same as TSPH, and we get something in the GD force that is more similar to the MFM method. I'm just going to quickly show basically the lower resolution case. Here we still get jets in GD force. Traditional SPH looks similar to what Hopkins and Raves found. Outflows look similar, but a bit slower. Then we reduce the magnetic field strength. We still get jets, and just as Hopkins and Raves found, but in traditional we do not get it, and we get a fragmentation of the disk. And then if we increase the magnetic energy, we still get jets, and we still get some, and we even get some outflows in traditional SPH. However, in Hopkins and Raves, they basically destroy the whole disk due to divergence errors. And this is a big problem. And basically, why this happens is that they use an old cleaning method, which is the Deadner cleaning. And here we can just see that our divergence is quite low because their divergence error is more of a factor of unity, actually. And yeah, I don't have time to show much more, so I will just leave the conclusions. Thank you.
Questions for Robert?
Go ahead. Well, I mean, it all comes down to the time step, basically. Adding the alpha wave speed to the shock, like to the Courant time step, basically. So there is no cost in actually doing the calculating the equations. But the problem is if you have very strong magnetic fields, then your time step will go down drastically. Yeah.
Got time for another question? No more? Okay, let's thank Robert once again. Okay, next we'll have Nicholas Cornot talking about intergalactic filaments.